In this module, we will see a kind of automata which can accept languages of infinite words. And these automata are called Bchi automata. Bchi is the name of the person who introduced this form of automata. So here is the goal. We would like to give some kind of an automaton for omega regular expressions. The normal NFA, DFA work for regular expressions. Now, can we come up with something like that for omega regular expressions? Once we have that, we want to take a synchronous product with the transition system of the model. Remember, when we were checking regular safety properties, we had our property in the form of an automaton, and then we took a synchronous product with the automaton representing the transition system. We moved all the labels to the edges and then made all states accepting, if you remember, and then we took a synchronous product. Once we did this, we checked for the emptiness of the product. So here we have a different story. We want an automaton model for omega regular expressions. That means for languages over infinite words. And then we want to take a similar product with the transition system. And then we want to be able to check the emptiness of this automaton. We will do a short recap of finite automata, and I will give some more definitions, after which we will extend these definitions to get our Bchi automata. Look at this NFA. This NFA accepts all words where the second last letter is A. Suppose I ask this question, is this word accepted by this automaton? Yes, indeed. How do we check this? We will run the automaton over this word. Let me explain what I mean by a run. This is one way of reading the word. You are at Q0, which is the initial state. On an A, there are two choices. Either you can stay here or the automaton can go here. Let us take the choice where the automaton stays here. So Q0, A, Q0. And again on a B, it stays in Q0. Well, for a B there is no choice. It has to stay here. You read a B in Q0, and on an A there are two choices. Either you read an A, either you go to the next state or you stay in the same state. This is a run where the automaton stays in the same state, and so on. In fact, in this entire run, the word is read while the automaton stays in Q0. Q0 is not an accepting state. However, there is another run where the automaton stays in Q0 till this point, till it reads a B, and on seeing this A, the automaton takes this transition, goes to Q1, and on a B, takes this transition to go to Q2. This run ends in an accepting state, and hence this run is called an accepting run. A word is accepted if there exists an accepting run. So for this word, here is an accepting run, and the language of this automaton is the set of words for which there exists an accepting run. Okay, the thing to note is that for this word there could be multiple runs depending on the non-determinism present here. This gives us a choice of taking the next transition. As long as there is one run which is accepting, the word is accepted by the NFA. Let us look at another word, A, B, 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 A. So this word is not in the language. Let us look at the runs. there is only one possibility. The only possible run stays in Q0 till the end. And since the ending state is not an accepting state, this run is non-accepting and the word is not accepted by this automaton. So this is giving us the criterion for accepting or not accepting a word. As long as there is one run which ends in an accepting state, the word is accepted by the automaton. In the case of finite words, you have an end. For example, for this word, the end is here at A. And hence we could talk about runs which end after reading this letter. We can say that a run is accepting if it ends in an accepting state. However, in the case of infinite words, there is no end. If we want to talk about automata for infinite words and we talk about runs, when would we call a run to be accepting? First of all, here our runs would be infinite. You would be running the automaton on the entire word. When do we call it an accepting run? Let us see. Take this automaton and take this word AB, AB, AA, and after a while it sees only B's. So this is an infinite word. Let's look at a run of this automaton on this word. So at Q0, when the automaton reads an A, it stays in Q0. When it reads a B, it goes to Q1. On an A, it comes back to Q0. On a B, it goes to Q1. On an A, it comes back to Q0. Stays in Q0 when it sees an A. And then on a B, it goes to Q1 and then it keeps staying in Q1 forever. So this is a word and this is an automaton and this is a run of the automaton on this word. When do we say that this run is accepting? Note that this is marked as an accepting state. When do we call this run to be accepting? We say that the run is accepting if some accepting state occurs infinitely often. Here there is only one accepting state, which is Q1. Look at this run. Q1 comes here, Q1 comes here, Q1 comes here forever. So Q1 comes infinitely often in this run. So this run will be called accepting. And since this word has an accepting run, this word would be accepted by this automaton. Note that we are now interested in finding automata for languages of infinite words. The first step would be to define the notion of acceptance. This is an example illustrating that we took a word which is infinite and we considered a run of the automaton on it. Here is a run and then this run contained the accepting state infinitely often. So we called this run as an accepting run. Let us see more examples. This is the same automaton. Look at this word AB, 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 AB and so on. Let us now run the automaton on this word. You start at Q0. On an A, the automaton stays at Q0. On a B, it goes to Q1. On an A, comes back to Q0, goes to Q1, Q0, Q1, Q0, Q1 and so on. Recall that a run is accepting if some accepting state occurs infinitely often. And in this run, Q1 occurs infinitely often. So this run is accepting and hence the above word is accepted by this automaton. We are slowly trying to understand the language of this automaton. Let us see another example. Suppose we have the word AB, AB followed by only A's. Look at the run. At Q0, on an A, you stay at Q0. On a B, go to Q1. Again on an A, come to Q0. On a B, go to Q1. And then you keep seeing A's. So for the first A, you come to Q0 and then you will stay at Q0 forever. Recall that the run is accepting if some accepting state occurs infinitely often. This is the only run for this word, and in this run, Q1 occurs up to this point only. After this, only Q0 occurs. So Q1 does not occur infinitely often. Hence, this word is not accepted by this automaton according to this condition. If you see, Q1 will occur infinitely often only when B occurs infinitely often. So this automaton, considered as an automaton over infinite words, would give you the language consisting of words where B occurs infinitely often. This is what is said here. So this is an automaton over infinite words, and it's called a Bchi automaton. So like non-deterministic finite automata, we have non-deterministic Bchi automata. You have states, transitions, initial and accepting states like an NFA. So here, in fact, this is deterministic even. But in general, you have states, transitions, initial and accepting states. The only difference is that Bchi automata are for infinite words. So there is a difference in the accepting condition. A word is said to be accepted if it has a run in which some accepting state occurs infinitely often. In the case of finite words, we said that if there is a run which ends in an accepting state, here we say that there should be a run where some accepting state occurs infinitely often. Let us see some examples. Suppose this is the language defined by the omega regular expression a par omega plus b par omega. So there are only two words, the infinite word consisting only of a's and the infinite word consisting only of b's. This is the NBA, non-deterministic Bchi automaton, accepting this language. If you look at A, it will start at Q0 and keep saying Q0 again and again. Since Q0 is accepting, A par omega will be accepted. Once you are in Q0, you cannot read a B. So no other word will be accepted apart from A par omega from Q0. If the automaton chooses to start from Q1, it can read only B, and since Q1 is an accepting state and it occurs infinitely often, B par omega will be accepted. Let us look at this language. A plus B star, A par omega. It says that you can read A, B some finitely many times, after which you should switch to a state where you read only A's. So this is what is happening here. You read A, B, as long as you stay here, rather if you stay here forever, Q1 does not occur at all. So if you keep staying here forever, that would be a non-accepting run. When can you go to Q1? You can choose an A and go to Q1, and once you do that, you can stay only in A. So for every word in this language, the moment you shift to A par omega, you have to shift to this state and keep reading only A's. And since Q1 occurs infinitely often, the word will be accepted. For example, if I look at the word B par omega, it is not in this language, so it should not be accepted by this automaton. Let us see. What would a run on B par omega be? There is only one run. You start from Q0. since there is only this transition on a B, you have to keep seeing Q0 again and again and again. And since Q0 is a non-accepting state, B power omega would not be accepted. Similarly, if B occurs infinitely often, you have to keep staying in Q0 because once you read an A, you cannot read a B. So this expression is giving us the language where B occurs only finitely often. Let us look at another example. A plus B star A, and then you jump to B power omega. So this is what is happening. You give the automaton for A plus B star A, and then you move to a state which will be accepting, and here you read only B's. So a word in this language would have an accepting run. This non-deterministic Bchi automaton corresponds to this omega regular expression. One more example. Here this entire thing has to repeat infinitely often. You should see a word in A plus B star AB, and again you should see a word in A plus B star AB, and again you should see a word in A plus B star AB, and so on. That is the meaning of this omega. So you draw the automaton A plus B star AB. Here I have made Q3 to be the accepting state. So the automaton has to keep looping around this if it wants to accept a word, and if it loops around this, then it will be A plus B star AB. We have seen this new concept called non-deterministic Bchi automata. This is a kind of automaton which is used for describing languages over infinite words. In particular, these automata would be useful to talk about properties described by omega regular expressions. Now, what is the difference from finite automata? Here, of course, you are talking about infinite words, and the word is accepted if there is a run which sees an accepting state infinitely often. Try to write your own regular expressions, omega regular expressions, and try to form non-deterministic Bchi automata for these expressions.